Okay, hello everyone. Since this is a bit of a mixed audience, I will start by introducing the things that I'm going to talk about. I mean, it's about quantum proofs of knowledge, but I want to make sure that everyone knows what I'm talking about without the word quantum first. It worked earlier. That's bad. That's worse. My computer seems to have crashed. Let's see whether I can. It seems to be alive in some way. Let's see.
It's doing an update or something.
Okay, now it's talks again to me. So, yeah, to introduce the concept and what I'm talking about, let me first say a few words about what is usually called post-quantum cryptography. So, in the area of post-quantum cryptography, we are interested in analyzing classical cryptography, so cryptographic protocols that do actually not involve quantum mechanics at all. So everyone uses classical computers, sends classical messages, etc. But we ask ourselves, are these protocols still secure if the attacker has quantum computers? So this is a very important question for all the things we use today, because the things we use today, they have to be classical. It's hard to market something that needs quantum computers, but we want them to be secure even when quantum computers come. And when you want to prove something or construct something that is secure in a post-quantum setting, you will actually need two different things. First, you will need quantum hard problems. So for example, many encryption schemes that we use today are based on, assume that factoring is hard, that discrete logarithms are hard, and so on. And those can't be used. They can be easily broken using a quantum computer. So we need new problems on which we base the security of the protocols. But it turns out that's not the only thing we need, although that's probably the more well-known thing one has to think about. The other thing is that we actually need also new security proofs. So a given construction, for example, classically, that would use some lattice assumptions to prove security, may still be insecure in the quantum setting because the security proofs we use in the classical setting, they often make transformations on the attacker that are not meaningful in a quantum setting. So the most common thing, and that which will also be interesting here, is that the state of the adversary is copied in some hypothetical execution, and that doesn't make sense for quantum adversaries. So it turns out that we need to revisit all the proofs, and it turns out in some cases it is highly non-obvious how to prove something secure. And one of the most well-known examples of where it gets highly non-trivial are zero-knowledge proofs. And for those who have never seen a zero-knowledge proof, I will show you what is probably the simplest zero-knowledge proof that is around, the zero-knowledge proof for graph isomorphism. And then I will explain what zero-knowledge means. So for the moment, just consider this picture. We have a prover and a verifier, and the prover, so there are two graphs, G and H, and the prover wants to convince the verifier that these two graphs are isomorphic. And we can use the following simple protocol. There it is. The prover takes one of the graphs, say graph G, and permutes it. So applies a random isomorphism to this graph and sends the permuted graph to the verifier. This permuted graph will not reveal much about this graph because it's shuffled, but we will see more formally why it doesn't reveal anything. Then the verifier picks one of these two graphs, so it picks either G or H, and tells to the prover which he has picked. And now the crucial step is that the prover either has to send an isomorphism between J and G, so between the permuted G and the original permuted J and the original G, or between J and H, depending on what the verifier wanted. And now you can convince yourself that this is if the prover can do this, it is kind of a proof. Because if G and H are not isomorphic, it means that no matter what the prover does, at least one of these two graphs will be not isomorphic to J, because they can't be both isomorphic. And therefore, with probability 1/2, the prover will not be able to answer this question down here. So this, even if the statement is wrong, the prover can cheat with probability 1/2, but there we can use standard amplification techniques like sequential repetition to get the success probability, the cheating probability down exponentially. So that's not a problem. So that's the kind of proofs we will have a look at. And now let me say something about the zero knowledge property. So zero knowledge means that the verifier doesn't learn anything. And how can we convince ourselves that this protocol does indeed not reveal anything about the interaction? Well, what we do is we construct a hypothetical machine, the simulator, which is able to simulate exactly the same messages as the verifier saw, but without interacting with the prover. So if we go back to this protocol, what you essentially have to do, I mean, I'm simplifying here, but essentially you pick a random graph, you pick either G or H, shuffle it randomly, then you get a graph J, which has the same distribution as this one, and then you know the isomorphism from this shuffled graph either to G or H, and then you make up the fact that you asked for that particular one, and then you have all the messages with the right distribution. So, I mean, we could prove this formally, but we won't because that's not the topic here. But the point is, you can construct a machine that simulates everything the verifier sees without interacting with the prover. And that means that the verifier doesn't learn anything, because if the only thing the verifier sees are messages he could have made up himself, then these messages will clearly not tell him something about the secrets of the prover, like the isomorphism between G and H. And that's the reason why this protocol is zero knowledge. And actually, even the term zero knowledge is defined in terms of having such a simulator. There's one subtlety here, yeah?
So can we go back to the previous?
Yes.
So something I don't quite understand. Why did, what was the role of J before we talked about zero knowledge?
The fact is that J will be, well, in the honest case, J is isomorphic to both of them, and we can just always show it's isomorphic to the one or the other. But in the dishonest case, when G and H are not isomorphic, then J cannot be isomorphic to both.
So couldn't we have, instead of providing an isomorphism between J and one of them, why are we not asking for an isomorphism just between G and H?
Because then we wouldn't be able to prove the zero knowledge property, because then we would get something So there are simpler protocols for this, because it's in NP, then there's always a very simple non-interactive protocol, but we want to make it a proof and to be zero knowledge at the same time. And that's probably the simplest protocol for that. Okay, but let me now say a bit more detailed how the simulator works in such a setting. And I will be a bit more general and talk about so-called sigma protocols, where we have three messages: commitment, challenge, and response. In many cases, the simulator will look more or less like this. He guesses first what the challenge will be. I mean, he has a probability of 1/2 of guessing correctly. I don't think so. Okay, so he has a probability of 1/2 of guessing the right challenge. So he just guesses what the verifier will ask here. And then he sends this first message called the commitment, which is the graph J, gets the challenge, which is the selection which one to open, and then he can respond if he used the right challenge. Because guessing the right challenge means he knows beforehand to which of the two graphs he will have to open. However, it may be that he guessed wrong, and then he just resets the verifier to the original state and tries again. And he does this in a loop until he guessed the challenge correctly and gets out of here. So that's how simulators, what simulators look like very often. And in particular, they look like this in the graph isomorphism protocol. However, in the quantum case, this does not work. Why? Because rewinding, like going back to an earlier state, implies copying of a quantum state. Because the verifier here has some state, some internal state, and that may be quantum. And running it and then going back to this state means I need to make a copy of that state, run, and then restore this copy. And this can't be done because it's, because of the no cloning theorem. So because of this, it was at first completely non-obvious whether these protocols are actually secure in the quantum setting at all. Fortunately, around I think 2006, John Watrous showed that a large class of protocols, including the kind of protocols I've just shown to you, actually are quantum zero knowledge because we can do a variant of the rewinding. So we cannot copy the state of the adversary, and because of what we have to do instead is when we want to go back in time, we have to uncompute what we did. So imagine you have this simulator sim that is like able to do one try and then needs to go back if he fails. So what we do is we run this one try simulator that tries to do a simulation, and then we measure whether this simulator succeeded or said I failed. And if it says I failed, we need to restore an earlier state, and this cannot be done by copying it. Instead, we just apply the inverse of the simulator. If the simulator is a unitary transformation, which we can always ensure, it means we can go back in time. This is not trivial because we have this measurement in between, so they don't cancel out. And this is where the non-triviality of this approach comes from. So you need to do some additional stuff and then go back, and then you can have this loop until you have success, and magically it turns to work out. And in the mathematics involved, you can see that what's happening is kind of similar to amplitude amplification.
Excuse me?
Yes?
Can you go back one slide?
Yes, because it's classical. That was your question, right?
So you're saying that basically he needs to copy some state.
This is what he does classically, how he does it classically. Yes.
So, but in this setting, if I understand correctly, this is the verifier's. The verifier should.
Yeah.
But he also can prepare the state size, so he has no problem copying.
No, well, there we would get very into the details of the definitions, but we assume that there is some initial state coming from the outside, like an auxiliary that represents the auxiliary information that the verifier may have over the world. And that is also given to the simulator, so the simulator does not get several copies. If you don't do that, you can change the definition and not do that. Then it might be easy to do a simulation, I'm not sure, but then you get into trouble when you want to use it as a sub-protocol, because if you have some earlier protocol run, this is not captured and you may have insecurities. So you have to do this in order for things to work out smoothly, and if you do it, you run into these problems and things don't work out smoothly. So, okay, so this is how you can prove the security of quantum zero knowledge protocols, so classical protocols, but you want them to be secure quantumly. However, there are some limitations of this approach that I would like to mention here because they come up later. So it works fine for the example I showed, but if we take it as a general technique, there are two limitations we have to be aware of. The first limitation is when we rewind the simulator, so when the simulator goes back to an earlier state by doing this uncomputation, then he forgets everything he has ever learned. Because we apply the inverse, so anything will be uncomputed. It can't be that the simulator finds out some interesting number and then after rewinding still knows that number. This is why I sometimes say that Watrous rewinding is an oblivious rewinding. We can say we want to try again, but if we do, we will even have forgotten that this is already the second try. And the simulator doesn't remember anything. And second, there's a technical condition that the success probability needs to be independent of the initial state. So the probability that one iteration of the simulator succeeds must be independent of the initial state. This is the case in the example we had because the probability is always 1/2 that he guesses the challenge right. but you can come up with situations where you have a simulator which can be sometimes a bit more successful than probability 1/2. And then suddenly we can't apply Watrous rewinding theorem. And the intuition, in my interpretation, is that the success, whether it succeeds, should carry no information about the initial state, because if it does carry no information, then measuring this would pull out information of the initial state and therefore disturb it. But that's just my intuition of it. And yeah, I forgot to mention, in this talk I will have these nice open problem stickers all the time when there is something where I think that I personally would find it quite interesting if someone, me or you, would solve it. So, like whether we can generalize this to cases where the success probability changes strongly depending on the state, I don't know anything. And later we will see, perhaps depending on the time, a place where it would be useful to have something like that. So, does this solve the question of quantum zero knowledge? Well, the rewinding techniques covers many important zero knowledge proofs, but it turns out it's not as powerful as classical rewinding. So one example that I like to mention in this case is the proof for graph non-isomorphism. I'm not going to show you this proof, but if you know it, it's one where it's kind of a, if you solve that, if you show that that one is quantum secure, you will probably solve a number of the open problem in the rest of this talks on the way. So that's an interesting one. So it doesn't cover all zero knowledge proofs, and it also does not cover so-called proofs of knowledge. So let me explain to you what proofs of knowledge are. So imagine we want to, let me give a use case. You have a digital passport which has a certificate on all your personal data on it, like a signature on something like Alice is born on this or that date. And now I want to log in somewhere and I want just to prove to the web service that I am at least 18.
I mean, if it's a cat, shouldn't it be proving it's at least 3 or something?
Indeed,
Sorry.
yeah, that's a good point. I should change the slide. I will remember that for the next talk. Okay, so, but this is something really adult, so even cats have to be 18. So how does the cat do that? The cat naively would say, oh, we use a zero knowledge proof. We show there is a signature on some date that is earlier than whatever was 18 years ago. And turns out this might be totally insecure. Why? Because the mathematical statement, there exists a signature on a message of a certain form, is always true. Because the signatures always exist. I mean, mathematically, we can't say something like, someone has issued this signature. We can just say, this number exists. Yeah? And it always exists, even if we don't know it. So a zero knowledge proof will be not useful for this, because the property of being a proof will only guarantee that a signature exists, not that the prover knows it. So therefore, we need something stronger. We need a way that the prover can not only prove that a signature exists, but he should be, or she should be able to prove that she knows this signature. Or in general, if you have some NP problem, you want to prove that you know a witness. Let me quickly go to the graph isomorphism again, just to illustrate that this is not, that is a reasonable thing to hope for. In this setting, for example, it's hard to come up with a way to do this interaction if I don't know an isomorphism for G, between G and H. Because I need to be able to go from J both to G and to H, and this I can only do if I have the isomorphism. And this is something we will formalize.
So in that case, it is a proof of knowledge?
This one is a proof of knowledge, yeah. Well, it's a classical proof of knowledge. It's open, but it's a quantum proof of knowledge, actually. But very similar protocols are also provably quantum proof of knowledge. As a side note, if the graphs are guaranteed to be rigid graphs, so if the graphs G and H are guaranteed to have trivial automorphism groups, then this is a quantum proof of knowledge. Okay, this is a lot of clicking. Okay, so the question is, how do we prove such a thing? I mean, I've been hand waving and saying the prover, if he succeeds, he should know the witness. But what does knowing even mean? So what we want is to capture this intuition. If the prover is successful, then the prover knows a witness. And now we want to replace this by something more formal. Let's first try the prover could output the witness. Yeah, we can't say something like the witness is in like a substring of his memory, because it might be obfuscated in some way. But what knowing intuitively means is, if I know something, it means that if you would ask me, I would be able to tell you. So this comes already closer to what we want, but it's a bit, it doesn't really mean anything, because the prover is a concrete algorithm, yeah, and the algorithm can't do anything else than what it's programmed to do. Yeah, it's like asking, I have a quicksort algorithm, and then I ask, can this also factorize? Yeah, this is not a meaningful question. No, the quicksort algorithm cannot factorize. Perhaps the computer can factorize, or the data I have to run the quicksort is sufficient to factorize, or something like this. But it doesn't make sense to ask whether the quicksort algorithm will factorize. Or it does make sense, and the answer is no. So we need to change this slightly. And the definition that cryptographers came up with is the following. Could compute witness is reformulated by saying there's some other machine that, given the prover state, could compute the witness. So there is a machine or an algorithm called an extractor that, given the prover state, can output the witness. So if I can come up with some machine that, given my state, can output a certain thing, then I say I knew this thing. Let's see. Yeah, first I give you the definition for those who are interested slightly more formally. So with quantifiers and so on. So there are variants of this with reordering quantifiers also, but let's use this one. So more formally, there is a polynomial time extractor E, so that for any malicious prover P star that tries to cheat, we have the following. If the malicious prover makes the verifier accept with some probability alpha, which is not very small, then we want that the extractor, when running the prover P star as a black box, so think of it as given as an oracle, that this extractor can now output a witness of the statement that is proven with some other not too small probability. And then we have some formula like how this probability of the prover succeeding relates to the probability of the extractor succeeding, but let's not worry about that right now. So this is just an abstract definition that models what we would like. But do we get that? Well, let's look at the...
What is the input of the extractor?
The extractor gets everything that the malicious prover would have. And he gets the malicious prover. So this means that if the extractor outputs a witness, it means the prover could also have output that witness, because he has exactly the same information to start with. There may be variants where the extractor has slightly more stuff, but that's not the setting we have here. Okay, so how do we construct extractors? Think again of a sigma protocol, so a protocol of the style like this graph isomorphism protocol. We have a commitment, a challenge, and a response. And we try now to construct an extractor as follows. The prover sends a commitment, for example, the graph J. Then we answer with a random challenge, as the verifier would, and then we get his response. So for example, in the graph isomorphism protocol, we would now have gotten the isomorphism between this commitment J and one of the two graphs. And then once we have that, we go back in time, so we rewind to this state here, and give the other challenge and get a response. And now we have an isomorphism to the other of the two graphs. So we have this situation. From J, we have an isomorphism to G and to H. So we can easily compute an isomorphism between G and H. And this is a way how, given the prover as a black box, we can extract a witness. And this property, so what we used here is the property of this interaction that if you have one commitment, so if you have two executions that have the same commitment but different challenges and both are correct, like accepting, then you can efficiently compute a witness from that. And this is called special soundness. Two different responses allow us to compute a witness. And graph isomorphism has this. We have just seen it, like two responses give us the two isomorphisms. And there are a lot of other protocols of that kind that have this property. And then you can generally state if a protocol has special soundness, then it is a proof of knowledge in the classical setting. Yes?
I'm sorry, could you remind me what the commitment is?
In the particular graph isomorphism example, there was a graph that is J that is isomorphic to both actually, because they are isomorphic. Yeah. So only in the dishonest case there's a difference. In the case where the prover is cheating, then it might be not isomorphic, but for the to one of them.
And the
Or to both.
verifier construct the commitment, or it won't work?
No, it's the prover sends that commitment. That's the task. I mean, in the proof of knowledge, we are now only considering like malicious provers anyway, because we want to show that they have to know something. Yes?
So for these proofs of knowledge, we're now implicitly assuming that the prover is computationally bounded, other than this NP witness that you may have somehow obtained.
No, there are different variants of that. There are so-called arguments of knowledge. There you make this assumption, but in proof of knowledge you do not make that assumption.
Okay.
However, it may be a bit confusing because an unbounded prover, you could say, an unbounded prover always knows the witness because it's determined by the graphs. What this guarantees is that no matter how unbounded the prover is, it will not be easier for him to do the proof than to actually compute the witness. Because the extractor is bounded.
Well, that's what I was wondering,
Yep.
because if the extractor is bounded, the prover might know the witness, but he could encode it in something that takes exponential time to decode. So the
Exactly,
extractor-
but the thing is we can always pull it out of the prover using this rewinding. So no matter what this guy does, if we ask him, for example, for the two graphs, and he produces the two graphs,
Yeah, yeah.
we know the witness. And the overhead, so essentially it says the overhead for getting the witness compared to just doing the proof is small.
Okay.
And this will, if you have special soundness, you can show that this always works. Essentially, the extraction probability will be quadratic up to stuff in the verification probability in the classical setting.
So when you have Oracle access to the prover for this particular extractor, you also need like an oracle that allows you to rewind. Like you can just imagine an oracle
Yeah.
that says, well, hey, you've already asked me this question.
Yeah. I mean, in the precise definitions, you could either say it's like we know the initial randomness, and we have a deterministic. We make it like say all the randomness is chosen at the beginning, and then you can just also rerun the whole thing to the same point. That's how it's sometimes done. That doesn't generalize to the quantum setting the way because we can't fix the randomness. Or you could have something where you could do snapshots. That would be in the classical setting be equivalent. In the quantum setting, we will assume that you have the inverse of the unitary operation that encodes the prover. Okay, what about quantum proofs of knowledge now? In the quantum case, we again can't do it that way because we know rewinding is not easy. We had this thing that we want to go, after getting the first response, we want to go back and get the second one. But since John has a rewinding techniques, we could ask, can we just apply it here? No, because as I mentioned, there's this oblivious property. If we rewind, well, that was about simulators, but technique is generally about rewinding some machine. So if the extractor tries to go back to an earlier state, so the extractor tries to go back here, he could try to apply John's technique, but since it's oblivious, he will be here and he will have forgotten the response because he's required to uncompute the response. So there's nothing gained because at the end he will just remember one execution. So we can't use the existing technique. And this is where my work starts. I proved that there is an alternative strategy how in certain cases, not in all cases, but how in certain cases. Sorry?
The restart, just stop it.
Well, I have 15 minutes to click restart later anyway. So, fortunately, next time it comes, I can actually leave it on because I think then it will reboot when I run out of time or something. Okay, so the classical extractor doesn't work because it uses copying and we can't even express that in the quantum setting. But we can try to do the next best thing. We can just assume that, there are a lot of issues, but whenever I want to go back, I just apply the inverse of whatever I can apply the inverse of, and the things that I don't have an inverse of, like the measurements, I just leave them. Yeah? So it's just a try whether it works. Yes?
Can you maybe make more precise this sort of no cloning argument about rewinding? Because it's not a copying in an unknown basis. I mean, okay.
Well, in the classical setting, it is not a copying of an unknown in an unknown basis. So if the prover would be a classical algorithm, then even in a quantum setting, you could rewind him because you could measure in a known basis his state. But in the general setting, the prover is malicious, and he might start with a quantum state in some basis, and we don't know in which one. And then the task, at least if we try to make a direct translation from the description of the classical procedure for extracting into the quantum procedure, there would be like the step, and now please clone. And of course, there could be variants of what cloning mean. You could perhaps try imperfect cloning and so on, but then you have to find out what happens. And all I'm saying is there's no direct translation because there's an unknown state involved.
But don't we need this rewinding to work only for honest provers?
No, I need it only for dishonest provers, actually.
For the proof of knowledge?
Yeah, for dishonest provers. Because what I want to prove is that, if I go back to this, I want to prove that if this prover sends this to the verifier, then this prover knows a signature. Well, I'm not so concerned with provers who are honest because I trust them to know the signature anyway. I'm more concerned with some prover who is under 3 and wants to claim I know a signature that I'm 18. And this should not be possible, so we will apply to that prover an extractor, get a witness, get the actual signature, and have a contradiction. So this is why we apply it always to malicious provers. Of course, we can also apply it to the honest prover, but that will be boring usually. Okay, so here's what I call the canonical extractor. I'm just doing everything I need and hope it will work. And then I analyze later whether it does. So what is the natural thing to do if I have a prover, a malicious prover, and I want to extract? Well, first I run the prover, which is unitary transformation, to do the first part of its computation where it outputs a commitment. Then I measure that commitment. Then I run the prover code again, another unitary transformation, and then I measure. I run the unitary transformation that represents the computation that the prover does if I give him some challenge 1. And then I can measure the response. So this thing is just a normal execution of the protocol. We run the prover, get a commitment, give a challenge, get a response. But now what we wanted, if we look at this picture, so we have done this, and now we want to go back to the point before we gave the challenge. So we just uncompute it. We apply, well, we can't undo this measurement, well, we could, but then we would forget the response, so we leave that, but we undo what the prover did here. So we apply the inverse of what the prover does given challenge 1, and then we assume that we are kind of in this state, and then we apply what the prover would do on challenge 2 and measure the response. And that way we get 2 interactions starting with the same commitment and with different challenges. And now we can analyze whether this actually works. So does this give us, because what we need is, we need 2 executions with the same commitment that we have, but both executions should be executions that are accepted by the verifier. I mean, we can anyway make up triples of values, but we need, like in the graph isomorphism example, we would need that in both executions here, the response is actually a correct isomorphism. And from these 2, we could construct the witness. So we need to make sure that this process here gives us 2 executions, assuming that that in a normal execution, the prover has some high success probability. Okay, does this work? Well, it's tricky, because we have at this point, well, we were hoping that this unitary and this unitary, they are inverses of each other, just cancel each other out. But that's not the case, because we have a measurement in between. And unitary measurement, inverse of the unitary, that you don't have any simplification rule for that, unless the unitary commutes with the measurement, but it does not in generally here. So if we have this measurement here, rewinding fails. And it's relatively easy to even construct particular provers where this extractor will fail. So you could just encode into this response some outcome of some measurement, and then you're in a totally different state and it doesn't go back. So it seems that this extractor does not work. But let's make it a thought experiment. Let's assume that this response has a length of only 1 bit. This may seem useless because there are no protocols where the response is only 1 bit. Because if there were, you could just guess the response easily and succeed in proving quite often. So there are no protocols with this property, but let's assume we have this. So the response is now only 1 bit. So this means that at this point here, we make a measurement of only 1 bit. And the less information we pull out of a quantum state, the less we disturb it. At least that's what we intuitively expect. Yeah. For example, if you have a measurement where the answer is already determined, that's a 0-bit measurement, then you just don't disturb the state at all. Here we have a 1-bit measurement, and if you do the math here, so the math of this is kind of the main technical thing, you find out, yep, it does work. So this disturbance is moderate enough so that the whole thing works out with somewhat different bounds than in the classical case, but it does work. Yes?
So how is it easy to see why measuring only 1 bit makes only moderate disturbance? Say that 1 bit could have been used to control a theory-wide operation, say erasing most of the things and throwing them away.
Yeah. It's essentially some playing around with linear algebra. I mean, don't have a clear intuition. It's just the less information you pull out, the less you disturb. And the thing is, the more likely this bit is to be the 1. I mean, if this has even less entropy than 1 bit, it gets even less disturbance. And the thing is, a prover that is often successful will have even less than 1 bit. Because if there are 2 right answers, but only one of them, if there are 2 answers, only one of them is the correct one, and we have a prover that is, for example, correct in 99% of the cases, then you have even less disturbance. So you need to do the math and see how big does the bias have to be here in this outcome so that the disturbance will be small. And then you need to see that the different cases, like there are different challenges, and you need to see that the sums behave nicely and so on. I don't have an intuition for that. We can show you the math, but can't do anything else.
How are you measuring disturbance? Is it like
I don't. I essentially have a proof that this whole thing works. So this disturbance thing is the intuition, and formally it's just I have a relation between the probability that it works until here to get a correct response and the probability it goes until here. That's all. That's what I have. So no. These sub things are just intuitive words. Yeah, but the thing is, we are in the thought experiment. We haven't solved anything. We don't have 1-bit responses. But what we can do is to make the response to be effectively 1 bit. How can we do that? The thing is, assume our sigma protocol has an additional property. Assume that for any for any commitment and any challenge, so there we are. The verifier is the prover is supposed to send some response, and there may be many responses that would be accepting, but assume we have managed to construct a protocol where there is exactly at most one valid response for any start of the interaction. So once commitment and challenge have been sent, there is at most one response. That does not mean that we send only 1 bit, and it can be that this response is hard to compute, but it has to be determined. And since these mathematics about measurements don't worry about whether it's easy to compute what we send, but only about the information content, having a response that is uniquely determined, in case it's valid, is essentially equivalent to having sending just one bit. Because essentially what we send is the information whether we are sending the right response or some other response. So this is what I call strict soundness. For any challenge, there's at most one response. And by using the same math as in the thought experiment, we can see if we have additionally this property of strict soundness, then this canonical extractor works. But there is this additional property of strict soundness, and it's an open problem whether this is actually necessary. But before you jump onto that one, we have almost solved it relative to some oracle, so don't duplicate work there. But if you have some answer like without oracles, that will be still very interesting. Or if we have a bug in the proof, then it will also be interesting. Okay. So here is a formal statement of what we actually get. So assuming we have special and strict soundness, then we know that the probability of extracting is at most the probability of verifying minus 1 over a square root of the number of challenges to the power of 3. This is a bit different from what we get in the classical setting. In the classical setting, the exponent here is 2, and this square root is not there. So the bound is worse. But this does not really change anything qualitatively. It essentially just will mean that if you want to amplify this to something with good quality, you need around twice as many rounds, which is, yeah, it's a minor thing. But whether you can improve this bound is another open problem. So I don't know whether it's necessarily. I mean, you get these worse bound because you have, in addition to what happens in the quantum setting, in the classical setting, you have this disturbance by measuring the response. And this disturbance gives you one factor more of this thing, essentially.
So in this graph isomorphism thing, the number of challenges is 2.
Mm-hmm.
How do you interpret the bound?
Then this would mean that if the verifier is has a success if the prover has a verify correctly probability that is noticeably bigger than 1 over square root of 2, then this means that there is a witness in his head, because then you could extract that witness with noticeable probability.
So as long as the right-hand side is positive,
yeah, well,
strictly you're
like,
fine, it doesn't matter?
I want it to be noticeable, like 1 over a polynomial.
So this cube, we don't really care.
Yeah.
But the
Well, we might can specific applications, but in the classical setting you can actually repeat the extractor to get this down, but we can't do that here, so it may be that there's a situation where the cube is worse than the square. But the square could also be worse than to the 1.
and so the square root, you'd expect this should not be there, or you think there's a...
I just say that my analysis, I would expect that the canonical extractor probably doesn't have it there. Has it there necessarily, but I don't have a proof of that.
But for this graph isomorphism, actually you said this doesn't apply.
Because it doesn't have strict soundness, you could have, between two graphs, you can have several isomorphisms. So that you would need that the automorphism group of both graphs are trivial, then it will have strict soundness. And then you will get all these kinds of properties.
Sorry, just one more.
Mm-hmm.
And you also did say you could modify this graph isomorphism protocol so that it has these properties.
Well, I can with computational assumptions. I don't have an unconditional variant of the graph isomorphism protocol that is secure. Okay, a second thing which is open here is computational security. So if these two properties hold only computationally, does the whole thing work out or not? And I think it doesn't. But that's actually related to this one. I think what techniques here also work here, but that's even less written up than what's here. So I'm just saying, probably there is some big trouble ahead if you try to make the whole thing work, if these things only hold against polynomial time adversaries. Yeah. The problem is, as mentioned before, the graph isomorphism proof does not have strict soundness in general. And it's an open problem whether you can prove the graph isomorphism protocol secure, or whether you can vary it in a way that doesn't use computational assumptions so that it becomes secure. An example of a proof that has strict soundness is the proof, a well-known proof for proving that you know a discrete logarithm, but that's boring in the quantum setting because the extractor can just compute the discrete logarithm. And I actually don't know any natural protocols that have strict soundness. But I mean, there are so many there might be some. I just don't know which one have.
Public with access?
Perhaps, yeah, I don't know. I mean, I'm just saying I'm not aware, but I would have to look at each protocol whether it is, it has it or not. I'm not saying there aren't. This is not open problem like finding others. This is just my lack of overview of all the zero knowledge proofs that are out there. But if we want to get zero knowledge for all languages in NP, we have Sigma protocols for all languages in NP, but I'm not aware of any that has on its own strict soundness. So what we can do in this case, at least for protocols where the number of challenges is polynomially bounded, and we can always achieve that, we can always cut down the number of challenges, then we can just, in the first message, the commitment, send additionally a commitment to all the answers I would give for all the different challenges. And if this commitment itself has the property that the opening information is uniquely determined, then what I get has, again, strict soundness. So if I have a property that I call strict binding, that means that I can open the commitment only in one way, so not only the thing inside, but even the information I make to prove that I opened it correctly. If that's both unique, then everything works out. I keep strict soundness. I add computational assumptions on the zero knowledge part, but we for zero knowledge for all of NP we need it anyway. And we get this by plugging these ideas and existing proof systems for Hamiltonian cycles and commitments from injective one-way functions together. We get, assuming injective quantum one-way functions, quantum zero knowledge proof of knowledge exists for all languages in NP. There's a caveat: we don't currently, as far as I know, have injective one-way functions that are quantum secure. So
that should be easily obtainable, though. I mean, if you just pick any kind of scrambling operation that maps n bits to, say, 3 n bits.
Yeah, I mean, you can probably just do something which is blowing up.
Yeah.
Let's say I don't know of any candidates where someone has actually proven that they're injective. If you use just some scrambling,
Right.
it might not be easy to prove that they're really injective.
Well, with all
But-
but exponentially
yeah.
small probability.
Yeah. So I guess like practically I would just accept as a candidate something like a hash function where I don't use the full input domain or something. Yeah. But we don't have any kind of nice candidates. We have just wild scrambling there, as far as I know. Yeah. So it would be interesting to have some more insights into this one. Hey, how much time do I have left? No? 10 minutes. Good. So now I have told you everything that I wrote down in the paper about quantum proofs of knowledge. But since then, I stumbled upon a number of things that are not as good as one would like. So where things that are easy in the classical case are not easy in the quantum case. Because let's try to actually use a quantum extractor to prove something non-trivial. And the first time I ran into trouble using a quantum proof of knowledge was when I proved something which I have here cut down to a minimal example. So assume we have a prover who is malicious and who has access to a signer. So someone signs to this prover arbitrary messages, except that the message 0 is never signed. So that's refused. This is some kind of simplified setting about this I'm proving my age thing, where I should want to prove that I'm... So here she wants to prove that she has a signature on... she gets a signature on anything except 0, for whatever reason. And now the prover is supposed to produce a proof that she knows a signature on 0. Yeah? So she has access to someone who signs anything except 0, and she tries to prove that she knows the signature of 0. Intuitively, you expect that it shouldn't be possible for a malicious prover to succeed in this proof, because she knows any signature except the signature on 0. So it should be that in this game, the probability that the verifier accepts is negligible. And how do we prove that? Well, let me prove it in the classical setting first, because there it's relatively easy. So assume you have a prover that succeeds in this interaction with non-negligible probability, and then we take the extractor. We know that there is an extractor where if I apply it to the prover, I get something that outputs a witness. So if I apply it to the prover, well, I can't apply it to the prover on its own, because from the point of view of the verifier, these two machines together are the prover. Yeah, that's what the verifier interacts with. It's the signer and the prover in one machine. So I give to the extractor prover and signer as a black box. And then using this rewinding stuff, the extractor manages to get a witness. So witness is a signature on 0. So by using the proof of knowledge property, we have constructed an extractor which outputs a signature on 0. But this extractor does not have direct access to the signing key. He has only access to this oracle here, internally, that does not sign the number 0. And from the security of signatures, it follows that you cannot get a signature of 0 if you have only access to a signing oracle that signs everything but 0. That's called existential unforgeability. So we have now an extractor that finds a signature on 0, given only signatures on non-0, and that's a contradiction. So this original prover cannot exist. What happens in the quantum setting? Let's try the same thing. There the extractor has access to the prover, so this thing, but he also uses the inverse of the prover, so the unitary transformation that is like the inverse. So now we have an extractor that uses essentially, well, this is boring, but he uses the signing oracle and uses the inverse of the signing oracle. And he finds a signature. Well, so what we have is an extractor that finds a signature given only someone who signs non-zero messages and the inverse of someone who signs only non-zero messages. And that gives a contradiction, that gives no contradiction. So the proof fails in this case. At the first glance, you may say, well, but the inverse of a signing oracle is also a signing oracle, because the signing oracle is stateless. And a stateless oracle is, you can build it by saying, like, input x and y, I make it into x, y XOR signature on x, and and this is self-inverse. So any stateless oracle is actually self-inverse, or can be made self-inverse, and therefore this problem wouldn't happen. But actually, if you try to do this in detail, you will notice a signing oracle is not stateless. Because, well, it may seem stateless, but the security definition, which talks about these, talks about messages that you have not, so it talks about the list of messages you have signed. So the signing oracle, actually, if you make everything formal, has a state, namely the list of messages that it signs. And the inverse will like unsign messages, and then you don't know anything anymore. So actually how to prove things like that is surprisingly open. Yeah. But with other things like I prove something about like this encryption contains a certain number, so in some settings it works smoothly, in other settings it doesn't. So that's a bit surprising. But similar things can also happen classically. I mean, if this would be some interactive oracle, then the whole thing would run into similar problems classically, except that there are more problems quantumly. Another thing where we have problems is if we use a zero-knowledge proof as a sub-protocol in some bigger protocol, we have sometimes this situation. So for example, if we construct a secure multi-party computation, we may start with with a passively secure protocol, and in every step we prove the message I'm sending now is the right message. And for this I use zero-knowledge protocol. So this makes actually a protocol that was secure against adversaries that are passive, that only listen to the messages, into one where even a cheating adversary that tries to send wrong messages cannot cheat, because he always needs to prove that he sends the right message without revealing anything, so zero knowledge. So, and if you go through the proof of such constructions, you have like some stuff happens, then you have the zero knowledge proof, and then some more stuff happens. And then at some point in the proof, you want to apply the extractor. So you will then have stuff happens, the extractor runs, more stuff happens. And then this side and this side, they should be indistinguishable. What happens if we plug in an extractor like the ones we have seen so far? Well, this extractor has then some non-negligible probability of, some noticeable probability of succeeding, but often it fails. So this thing will not be indistinguishable from this thing, because this fails often and this doesn't. Classically, no problem. If the extractor fails, we try again. We amplify the success probability by just restarting the extractor a lot of times. In the quantum setting, how can we do that? Well, it seems we have the tool for that. because here we want oblivious rewinding. We have an extractor that failed, so we want to let it try again. So it seems we can use Watrous technique. But no, this is oblivious, but we had the second limitation that the success should be independent of the initial state. And here we have an if you look at this extractor, here we have a minimum. Like we can show, for example, that always at least probability 1/4 of succeeding. But there could be some initial states where it has more success. Yeah, we don't have an upper bound. Success can go up and down between something and 1. And therefore, we at least cannot apply the theorem from Watrous' paper. It might be that the algorithm there works here, but we don't know it. So how you make an extractor like output the witness in longer runtime with higher probability is an open problem. It should appear here. And this applies, for example, to the GMW compiler that I just mentioned that makes passive protocols actively secure. But also in the graph non-isomorphism proof that I mentioned already, same problem occurs because there you use an extractor in the proof of the zero knowledge property. I mean, this sounds weird, but if you look at the protocol, it makes sense. So this is another case where classically it works fine, but quantumly we don't know anything yet. So let me conclude. I mean, there are even more open problems when you come to things in the random oracle model, but I don't have another hour, so I won't say that. So let me conclude. What I've shown you is that zero knowledge and proofs of knowledge are objects that bring us a lot of new challenges in the quantum setting. And in some basic situations, we have solved these things. But there are many unsolved issues. And one kind of challenge that I issue is like proof graph non-isomorphism secure, because I think that on the way you will find out about a lot of things about that are useful for other protocols. And it's important to study these things because these problems are not restricted to zero knowledge and proofs of knowledge. All the times in crypto, these things appear again the same problems. So in cryptography, zero knowledge and proofs of knowledge are kind of the Drosophila of cryptography. A lot of the challenging things that happen in cryptography can be investigated in the simplest setting when you look at zero knowledge and at proofs of knowledge. And you get the really hard settings when you start doing multi-party computation or other wilder things. So we should first kind of understand them on the basic level, and then we can go to the advanced problems. Okay, that's it, and I thank for your attention.
Questions?
What about proof of knowledge of quantum state or QMA?
I don't know anything. So it's an interesting question. Can you do, well, there are two interesting things. One is you have a classical fact you want to prove. Yes, a language, but you want to use quantum interaction. Interesting question whether you can do more or not, but I haven't worked on that, so I don't really know. And the other question is you have actually a quantum state, so your language is quantum. You want to prove this quantum state has a certain property. I also don't know. Well, actually you get things like that to some extent as a, there are some results, I forgot like the authors, but there are by now results on multi-party computation on quantum states. And if you use these protocols, actually they specialize down to something that should be computational, like that should have these things in a computational setting. But you get protocols with much higher round complexity and only computation security and possibly more assumptions. So it doesn't really, it's like much bigger protocols than you might need. But there are some solutions that would give you some results in that direction. Yeah.
When you discuss this problem with using the proof of knowledge as part of a larger protocol, like when you could get a signature of 0 from signatures of non-zero things, if I understand the problem correctly, is that because you're only allowed to query your signature oracle classically? You weren't allowed to query in quantum superposition?
No, but I kind of...
Like, if you had a signature oracle which was secure when queried in quantum superposition, would you not be able to just go through the analysis then?
But the problem is that you still have this message log of what are fresh messages. Because the security of signature says you cannot produce a signature that you haven't queried.
Yes.
But so you get that, then you get already in a lot of definitional issues. And similarly,
The signature scheme is stateless. There's no.
Yeah.
You don't actually have to
yeah,
use
the
it for
signature scheme is stateless, but and I think that that particular scaled down example that I showed you, where it's always non-zero, then I think it would actually work out even without querying it in superposition. But if you have something like you want to guarantee that the prover does not prove that he knows any signature that he hasn't queried, then you will need a oracle that signs everything. But you will need, well, perhaps not the oracle, but someone in the definition of what we do will make a list of messages that we queried. And you may not call it part of the oracle, but you will see that this thing will be rewound too. And then, I'm not. It may be that the work that has been done on signatures where you can query in superposition and have security, it can be that this gives us something here, but it's not obvious. So I don't see that it would, but I also don't see that it wouldn't. I don't even see that a normal signature scheme wouldn't work here. I mean, I only wasn't able to prove it.
Announcement?
13 minutes left here.
Well, before the break, I just wanted to make a quick announcement. So since this came up this morning, so on the schedule for Friday afternoon, there's something that's called drum session or discussion session or wrap-up session. So I think we have like an hour and a half scheduled for this. So I just want to invite all of you to think of anything you want to bring up. So this could be a result you want to mention or a question that you want to ask to the audience before everyone disappears. You have all these experts available for you, or just some discussion point you want to bring up. So as long as it fits in under 5 minutes, it's good. So just to keep it sort of organized, we'd ask that you get in touch with either Dorit or John or myself, or send me an email just to say, I'd like to say something about this, and then we'll just collect names, and then that will give us an idea of what's going to happen during the session.
Okay, so let's thank Dominique again, and